Hi there. So today I'm not going to give you any worksheets. Yay! Instead it's going to be video after video after video. You still have to take your notes, but I'm not in class to give you demos for these phenomena, so I'm going to have to show you some videos after this video to help explain the phenomena of wave behaviors. Yeah, you can see that up there, wave behaviors. Alright. Sip of water to get started. And here we go. We're talking about wave behaviors today. The first behavior we're going to talk about is reflection. It is defined as waves will bounce off of any surface they encounter. So I want you to put that right here where it says reflection. Plenty of space to write 2 little lines of text. Pause if you need to, finish writing it down, and I am moving on. Sound waves do what we call that an echo. One of your videos down below is why do we have echoes? It's a fun little 3-minute-ish video about echoes. Watch it. You'll learn about echoes. In fact, the only reason you can see anything is because light is also a wave and it bounces off of things. And then that bounced off light comes into our eyes. More about that when we talk about electromagnetic waves. Alright, so the law of reflection. Everything that reflects, so every wave, follows the law of reflection. Waves bounce off of a surface at an angle that is equal to the angle at which it hits the surface. So pause, write that down, right above that picture on your notes, which is, well, I mean, y'all can see it, but still right up here. And then come back to me. Okay, I assume you've come back to me now. So when I say that a wave bounces off at an angle equal to the angle at which it hit the surface, I'm talking about these angles in here. Not the angle between the sound wave or the light wave or whatever and the surface itself. Not this angle and not this angle, but these two in here. This dotted line is something you need to know. You need to make a space for it somewhere on your note sheet and write down the word normal. And then write down this definition. A normal line is an imaginary line at right angles to a surface. I'm not going to repeat it over and over again like I would in class because y'all can pause and go back and do it yourselves. Ha 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 ha. I don't have to repeat myself. Alright, so if you need to pause now. Did you rewind enough times to get it? Alright, so this angle right here is the angle of incidence. It's this angle that equals this angle over here, the angle of reflection. Normal line. Just measure off the normal, not off the surface. Now, those of you that know a little bit about angles in geometry will know that, well, this angle over here equals that angle over there in this picture. Well, yes. Yes, it does. But this picture has something very uncommon in the universe, a perfectly flat surface, a mirror. Not every surface is perfectly flat. So this angle down here will not always not always equal this angle over here. Alright? Okay, let's move on. Refraction is the next thing. Definition of refraction. The bending of a wave as it passes from one medium into another because it changed its speed in the new medium. When light goes into a more dense medium, it slows down. When it goes into a less dense medium, it speeds up. As it changes speed, it also changes direction. If we were in class, I could explain that to you, how it works. Don't worry about it. Just know that it happens. If you want to know how it happens, go hit YouTube to find something a little higher level than I'm showing you. Alright? So there is a video that goes with diffraction. It's why does a pencil look bent? That should be in the links below the link for this video. Go watch it when you're done with this. It's fun too. The greater the change in speed, the more the wave bends. Alrighty. Now, you can see here, and again, when we're measuring the angle, we're measuring the angle off the normal, that imaginary line at right angles to the surface. This right here is the surface between air and glass. This is the surface between air and water. Coming in at 60 degrees from the normal, goes into the glass. It's now 34.5 degrees from normal. It bent towards the normal line. When light comes out from the glass, it bends away from the normal line back to 60 degrees. Same here, from 60 to 40.6, from 40.6 back to 60. Those of you who know geometry know that this angle here is also 40.6, right? Of course, right. So, what you need to know, the more dense the medium, the more the light bends. So the greater the change in density, the greater the bending. Alright. I'm not going to worry about this. I'm not going to worry about this. I'm not going to worry about this. I mean, if you want to pause and write it down, you can. But we're not in class. Let's just make this a little easier, shall we? Okay. Moving on to diffraction. Alright. I have a very short video about this. It's just a video of waves coming through a seawall and they bend and spread outwards. Diffraction is the bending of a wave around an obstacle. When waves hit an obstacle, some will bounce off, of course, but if the obstacle doesn't complete, like a wall in a room or something, like if it's just a seawall with a gap in it, the wave's energy will go through the gap and expand outwards. It'll bend around. As you can see here, we have a single obstacle. The waves go around it, so you can see the bending right there. These 4 images are images from a wave tank, very shallow water, and a light source underneath it and a camera above it looking down, and you have something that makes waves going across it. So you can see how the waves make the light ripple. And you can see how the waves bend around the obstacle. Bending here. When you have 2 obstacles in a gap, like a seawall, across a bay to protect it from storms, you see how they bend around and around. So even though you're on the other side, you still get some wave action. Alright? Same down here. Now, the next image in this slideshow is a GIF, I don't care how you pronounce it, a GIF file from tsunami back in 2004. This is part of the island nation of Sumatra here. There was a big old earthquake, plates moved, one plate went way down, water rushed in, and then bounced back up, and you have a tsunami. There's 2 pulses to the tsunami. They're red and they're blue here. So you can see this island here is Sri Lanka. This is India up here. Vietnam is over here. Somewhere way down and to the right would be Australia. So this is the Indian Ocean. This is the island of Sri Lanka. And as you see, the waves hit here and they actually go around to the backside. So people on the backside of the island did not get completely shielded from the tsunami. It wasn't as bad for them, but they still got some of the energy from the wave. You can also see reflection here too, going off that way. So waves in this particular picture, they're reflecting and diffracting. Cool. Alrighty then. Interference is the next concept. And we have a lengthy video after this one about interference called the original double slit experiment. It's a combination of diffraction and interference. Alright, and the guy doing it explains it perfectly. It's not a funny one like the first 2. It's not just a boring seawall thing like the second one, like the third one rather. This one's pretty good. It's not too terribly in depth, but it explains things nicely. So the definition of interference is when 2 or more waves overlap and combine to form a new wave. There are 2 types of interference, constructive and destructive. Which one do you think means makes bigger waves? That's right, constructive. In constructive interference, the waves combine and add to each other. For transverse waves, it means the crest of one lines up with the crest of the other, and the trough of one lines up with the trough of another. Alright? For compressional waves, it means the compressions of one line up with the compressions of another wave, and their rarefactions also line up. Pause. Right. Come back to me. Okay. I believe I put this picture in the notes, didn't I? Nope, didn't put this one in there. Okay, so you have 2 transverse pulses coming towards each other where they meet on the same side, so they add and make a bigger pulse, a bigger amplitude. Wakes up the bird. And then each one goes a separate way. So this pulse here is that pulse there. This one here is that one there. Energy is not made out of matter, but energy is something that affects matter and can travel through matter. Waves don't bounce off each other. Waves are just transported energy. They can move through each other, but the matter has to do what both waves say at the same time. That's why you have a twice as large crest right here. Alrighty then. Destructive interference, the two waves meet in such a way that they cancel each other out. Pause, write it down, then come back. In transverse waves, it means that the crests of one wave line up with the troughs of another wave. So one wave's telling the medium to go up, the other wave's telling the medium to go down. The medium just doesn't move. Or it moves less than it would, let's put it that way. Compressional waves, rarefactions of one wave will line up with the compressions of another and cancel them out. So the medium is being compressed by one wave and stretched out by the other wave, and the medium just doesn't move. Okay, so next picture shows you the birdie on the wire again with the crest of one wave and the trough of another coming together. Where they meet, they cancel out. And the bird goes back to sleep. And here goes the crest going on its way, here goes the trough going on its way, ignoring each other. The medium, the matter, cannot ignore the waves, but they can ignore each other. You have the same picture on yours, but it's probably no red, there's gray. So this is constructive interference. Wave A, wave B add up together to make sum of A and B, which is taller crests and deeper troughs. Here, wave A and B are lined up so that they're destructively interfering with each other, but they're not the same size, so they don't completely destroy each other. So you get the red line, sum of A and B, which is, not as high a crest, not as deep a trough as it would be if it was just A. Alright. That is the end of the slideshow. So go on to watch those other videos, enjoy them. And that's all I want you to do today. Y'all have a good day, alright? Bye-bye.